All right, one last video down here. It's a couple days later now, and I've actually gotten all my data put together and have done a rough cut on sample calculations. I wanted to come back here and just give one more quick video on the exact flow path during the experiment for task 3 and how exactly that's going to be run. So we have our pump. Pump's off right now, but it's going to be running. We are accounting for the start of our overall piping system starting right here. So it's about the same place we're measuring our pump outlet. We're going to go through all of the piping. We're going to bypass our filter. So the flow will go through this diverter valve. So what the internals of this diverter valve look like, I don't know, but there's some kind of tortuous path that the water has to flow through. So we're going to treat this as some kind of weird fitting. We do not know what the equivalent L over D is for this device, but we're going to calculate it. All right, I'll come back to that in a couple of minutes. So this is an unknown as far as taking inventory of all the losses in your piping system. We'll continue through the rest of the piping system, which has straight sections and elbows and valves treated as T's, etc. Right? And that's all inventoried for you, and you should be able to account for every one of those losses. So before we leave the pool house through the wall and into our underground section, we go through this diverter valve. Let me run this over. So I'm going to divert all of my flow coming in through the diverter valve, out through this ball valve, out to the fountain loop. Okay. We're going to run an experiment where we run with the ball valve full open, 100% open, and we're going to treat that ball valve as a 12-inch length of equivalent pipe, essentially just as a piece of straight pipe, because that ball valve itself isn't much shorter than 12 inches. So that's how we're going to treat that. That's an estimate, right? Everything else we're doing here is an estimate. For example, we're treating these fittings as straight pipe. We're treating a chlorinator as straight pipe. We're estimating what's going on with this check valve. We have a rough approximation for how that three-way valve operates. We're treating it as a T with branch flow. So there's a lot of potential for error in our estimate. So if you think about how we're calculating this, we have a friction factor. Friction factor is an estimate from the Moody diagram for turbulent flow. So there's potentially a decent amount of error involved there. Right, the E over D, we're taking a rough guess at what the roughness of PVC pipe is. So there's room for error there when we go to the Moody diagram. Our fittings, right, we're approximating that. Let's see, we have an L over D, right? So there's potential error there for all of those things. And we also have a V squared over 2. So V is the average flow velocity. That's based off of our flow rate measurements. I would actually say there's probably a decent degree of accuracy in that measurement. If you look at the 3 repeats I took for filling my bucket, I was pretty good on the repeatability of timing how long it took to fill the bucket. Now there is a little bit of error in my bucket filling because when I have very high flow rates, that water sloshes around a lot. There's a lot of air that gets entrained in there, and I don't quite fill the bucket 100% at the time that the water's sloshing out of there. When I pull the pipe away, it's actually short a little bit from full. So there's a little bit of error there on my flow rate measurement as well. The point of this is that there's a decent amount of error here, right? So if your results come out to be a little weird, you should not be all that surprised. So going back to this experiment, we're going to turn on the pump. We're going to measure pressure right here. We're going to have this ball valve wide open and everything else in the system is wide open. So we're maximizing the flow through this leg for this particular experiment, and we're going to get some flow rate at some outlet pressure. We should be able to calculate the pressure drop, the expected pressure drop across the entire system for everything except the diverter valve. So if we have delta P equals the sum of all our system losses, we're going to measure delta P. It's our outlet pressure minus 0 PSI gauge atmospheric at the outlet of our piping system. That's delta P on the left side of the equation. The right side is going to be all our major and minor losses plus our static head plus our diverter valve. The diverter valve is the one unknown in that equation. We will solve for how much pressure was lost across the diverter valve and back calculate what the equivalent L over D should be for that. Now realize with the error that's in this system and all our piping inventory, etc., we might get a very unreasonable value for that L over D. It might be unusually high. It might be very, very close to zero. It might even be negative. And what it means if it's negative, that means we've probably overestimated all of the losses in our fittings throughout our system. And so you have to think about what kinds of errors may have caused us to overestimate that. If you do get an L over D that is negative, what I would say is just assume that it is zero and calculate your system resistance curve for various flow rates using that equivalent L over D of 0. All right, I'll leave it at that. Hopefully everybody will figure everything out and it'll work out well for us. Email me if you have any questions.